And I know it's a bit hectic session for many of you because you are at a stage listening 4 hours session and on this holiday, right? Saturday. And I'm very sorry. So I hope you will enjoy this session and you already enjoyed the previous sessions from the speaker. And
Sorry to interrupt you. Would you be taking the questions on your own, or do you want help from our side?
I'll be taking my own. So,
Okay.
yeah, participants, you can post all your questions on the chat box, and I am using multiple screen. So, especially for chat box, I kept one monitor, so
Sure.
I'll be interacting while I'll be covering the sessions. Okay, so feel free to
Sure.
ask any question. Yeah,
Yeah. So after 50 to 55 minutes, we can have 5 minutes break.
break.
Yeah.
Sure,
Sure. Thank you.
sure, sure. Yeah. So today and tomorrow I'll be taking two sessions, mainly one session named as the quantum Shannon information theory, and I'll be taking one more sessions tomorrow on quantum channel specifically, which is an important topic for quantum communication, as well as an important theory called the no cloning theory. No cloning theorem. So I'll be covering these two parts tomorrow, and if time permits, we'll also see some examples in Qiskit on quantum teleportations, if time permits. Teleportation. So if you look at textbook specifically, let me refer some of the important textbook material first before in fact going to the session. So where from you should study, right? So those who are very new to quantum computing and quantum informations, just a beginner, for them one of the best book is by quantum computing. So let me first write the references. Okay, quantum computation and quantum information, and this book is written by Nelson and Chuang. And another book that we'll be following is by Mark J. Wild or Mark Wild. So this book, the name of the book is Quantum Information Theory. I'm referring some more books. Another book known as the Quantum Systems Channel and Information by um, Holivo. Okay, I'm just to save time, I'm just writing the author's name. Okay, just type quantum information or quantum system channel and information book. Okay, so by Holivo. And there is another good information book on quantum information theory by Hayase. So it is in 2017, I think. This book, one of the standard version is 2010. And Mark J. Wild, you can read the second edition or the 2013 edition is fine, right? So these are four important reference, and there is another reference book also by Watrous, and Watrous is associated with IBM. So this is another important book. So by John Watrous, so 2018 versions you can have a look. So at least these are the main two references for these sessions. However, these are important other books for quantum information theory, especially Shannon quantum information theory and several extension. So and the outcome of these sessions, although you may so two aspects. Okay, so two aspects of this course where this knowledge will be applicable, skills will be applicable that we'll be learning from this course, right? Today and tomorrow. So two part is there. One is the computing part of communication, right? So this part, because I'll be stress this part, okay, because I am coming from the computation background. The way I'll be delivering the session will be bit different than it will be delivered from a quantum computer communication person, right? And that is a information side or the communication side, okay, aspect. So So what I'll be delivering today and tomorrow will be the computation part of the Shannon information side. Although I'll be sharing the notes, and some of the notes are covering mainly the information part, where you will see the definition of entropy, like quantum entropy or the Shannon. Yeah, here we call von Neumann entropy. Okay, von Neumann entropy, and so on. So and mutual information, mutual entropy. So these are various definitions, various concepts like fidelity. Okay, so these are the aspects are there and how they are defined, several examples. So this part I'll be providing you notes. I won't go with the definition part, but I'll be focusing on the computation part, and mostly on the concept. Okay, so how the things are built on. Now, where these things will be useful, so two part. One is, of course, those who are interested in working with the quantum error correction, which is a very important topic, right? Error correction. So this is an important end goal, and I am not a person in this genre, at least till now. I don't have a single research paper in this direction, but I'll show that how this quantum information side that I'll be covering, the computation part, basic fundamental part of quantum information theory, that will be useful in error correcting code. So error correcting code, especially those who will start this topic on error correcting code. So especially the repetition code, or SOAR code, right? So these are several initial code, although there are very nowadays people work on the surface code and all, right? So there are lots of good like error correcting code theory, right? And they are using a lot of theories from quantum information side, but at least the some of the portions of today's class and tomorrow's class will be very much useful for repetition code and source code, although they are not used nowadays. Okay, so this is one part where this course will be useful, right? So because the qubits are erroneous, right? And if you design an algorithm to solve a problem, suppose you have a problem P, and you design an algorithm to solve the problem, you have a solution, right? And your solution has certain uncertainty, right, due to the noise of the hardware, right? Or the error when you encode the problem into the qubit, right, quantum information, then you do the simulation as well as you do the measurement. So every aspect there is some uncertainty in form of noise or otherwise. Um, in different way. So how you work on that? So how you are sure about, suppose you receive a information in bit string, say 1010, right? In a particular when you represent your information in 4 qubit quantum state, and this is the quantum state, you get the probability say 0.89, right? And other qubits say less than that. How much you are sure that this is your answer qubit, right? Or this is the solution state. So so how you basically design certain error correcting code to solve that, that is one aspect. Next aspect is the how to treat with error, right? So there are topics called the error mitigation, which presently those who amongst you use the just for algorithmic purpose use some simulator or especially quantum hardware, they see that when you run your algorithm for over 20 qubits, say as an example, so your results sometimes may not be meaningful, especially for quantum machine learning applications or those kind of things. So there you will see that the information that you are retrieving for classifications, for several tasks, learning tasks, predictions, etc. So you are mathematically you are 100% correct that you design some unitary operator as an algorithm, and your problem encoded as a state psi. You have an output state phi, and then you do quantum measurement, and you get a classical state C, right? Now, the C that you retrieve from your encoded state, I'm sorry, encoded state C. Now, how much correct this C is, right? So, of course, C is noisy, right? And to mitigate this noisy C to an estimate C hat, where C hat is basically the C actual or the C predicted, right? This norm should be as close, as less as possible, right? So to do that, we design various circuitry, quantum circuitry here to mitigate this kind of error, right? And those kind of sets of algorithm are known as the error mitigation algorithm, right? For example, those who amongst you are using the Qiskit as your programming software, you see that there are protocol like ZNE, zero noise extrapolations, or PEC, right? Probabilistic error cancellation. So these are some of the methods used in this kind of error mitigation techniques to basically see that your estimated information is as close as possible to the actual curve, right? So suppose you got a, result like the histogram, right? I'm drawing in a continuous way. So suppose this is the answer you got, right? This is your actual answer you are expected to get, but the result that you actually are getting something like this, right? So how to maximize the probability from here to here, right? So this probability, the informations getting the increasing the probability through certain way, the probability of your actual measurement basis or the solving basis is a way of doing the algorithm better and better. And that particular set of methods called the error mitigations method. So this is one implication. This is the second implications. And the third one is so how to treat or how to model noise, right? How to model noise. So those who already work on the classical communication theory, right, or the classical communication system, you have a lot of noise model, right, channel model. So if you have a X transmitted data from one place and Y received data in another place, maybe it's a single input, single output system, or a MIMO system, for example, multiple input and multiple output system. And you know that there is a particular loss, right, channel loss H, as well as you may have some additive noise part here, right? So your actual information that if you put here Y as your actual information, so that is you write as a Hx plus W part, right? And this is how you write your information Y equals to Hx plus W, right? And when you model it in a matrix vector form, typically you write as a Y as your Hx plus WH now becomes as a matrix and W as a vector, right? So now how when we treat the quantum mechanical model, how to model the error and all to consider the realistic picture, right? So all these are the aspects or the outcome of this session, right? And I will be focusing on the computation part as well as some of the implications, okay? And of course, I'll be deviating from the actual theory or the concept by definitions and all. I'll be sharing the notes, okay? So with this, um, now we have two parts. First is the noiseless case, noiseless picture. So this is the part one. And part two, that is the noisy case, noisy picture, when something will be coming, that is the quantum channel part. I'll be coming tomorrow, okay? This is for noisy picture. Because to understand the noisy picture, we have to first understand the noiseless picture. So likewise, those who are already working on some of the quantum circuits and quantum algorithms, because many of you already covered the QT1 to QT5, and you already have drawn circuits. So what you have done, you have three main steps, right? So one is the state preparation. State preparation, that is you encoded a state in gate psi. those how to do this. Suppose you have a classical data. Suppose 1, 2, 3, 4. This is your classical data A, right? Now it can be a column vector, so I'm writing as a transpose of this, right? Or you can take the row vector, whatever form you want to take, that's fine. Now, so first, what we'll be doing? We'll be doing the these A2 first. We have to design the Ket A part, right? How to do that? So A by norm A, right? So now 1 by, if you take the square of all these things, so 1 square plus 2 square plus 3 square plus 4 square, and then you normalize these data sets, right? And suppose you get A0, A1, A2, and A3, right? So 4 data points you have taken. So how many minimum qubits you need to do? So if you are following, there are various encoding techniques, and one of the encoding techniques is amplitude encoding, right? Amplitude encoding. So then you have 2 qubit. So you minimum how many qubits you need? You have 4 data. So the formula is log n 2 base ceiling functions, right? Is the minimum number of qubit you required for amplitude encoding. So here we have 4 data points. So log 2 base 4. So we need at least 2 qubits, right? So 2 qubits has how many states? Q0 and Q1. They have 4 state, 0, 0, 0, 1, 1, 0, and 1, 1. And I have to store this 4 amplitude as a probability amplitude in front of this A0, A1, A2, A3. So A0 times 0, 0, this is the basis vector. A1 times 0, 1 is the basis vector. A2 times 1, 0, and A3 times 1, 1. So your final quantum state will be, Ket psi will be the summation of all this state, this AI Ket I, right? And I varies from 1 to 0 to 3, right? So it will be A0, 0, 0 plus A1, 0, 1 plus A2, 1, 0 plus A3, A3, sorry, 1, 1, right? And this is the way how you encode the information first. This is the first step we do to start with from classical to quantum, but this is the first step that we do. So this is the exact encoding we do with the state encoding technique. And in Qiskit, we use qc.initialize, right, as a function. So qc is your quantum circuit. So you define the qc, and this is the functions you can call. And if you put your vector, a vector here, so it will generate a variable. So this is qc equals to qc initialize functions. If you call, it will generate a circuit for you, okay, for this state. So this is the first step we do. Then you design an algorithm, and that algorithm has a unitary representation, matrix representation for your algorithm, right? It can be quantum Fourier transform, it can be quantum phase estimation, it can be variational quantum solver, QAOA, or whatever, right? So ultimately, it's a unitary set of matrix, big matrix, right? And ultimately, what we have so here at this point we have u psi, right? And then we are doing the measurement part, right? We are getting classical value. So in a basic engineering system, what we do, we have an input X, we have a system A, and we have an output Y, right? Similarly, the channel model we have seen, just simply X you are transmitting, passing through a channel X, and you are getting Y. And suppose they are vector data, and this is a matrix, so you are getting Y equals to HX. This is your model, right? Even without the additive noise, right? Here you can't do the additive noise, so the treatment is different, and we'll see it tomorrow. But I'll introduce the density matrix today, and that will be helpful to understand tomorrow. Sorry. So here we write it as this pen is creating a lot of trouble. Y equals to AX, but here I am starting with psi, evolving with U, and I am again another state phi, where phi equals to U psi. This is the difference from these things. So So now this is any vector. This is just a unit norm complex vector, right? Unit norm or normalized vector, unit norm complex vector, right? And then you have this matrix is a special matrix called the unitary matrix. And their relation, why it is unitary, solving the Schrodinger equation, I already covered in my previous QTs, and you have already looked that particular part. But here it can be any vector, right? It can be any matrix. So that's the basic mathematical way of distinguishing the quantum, like the quantum communication model, or the quantum, the computation part of the quantum communication model. This is the basic difference of the model. Now, tomorrow we'll see something called the ensemble versions of that. So if you have a like, uncertainty in this state psi, that the informations that you create in your qubit, like from 1 2 3 4 on the quantum qubit state, as with the amplitude a0, a1, a2, and a3, you will see how you are creating the informations either on the superconducting this oscillators. Like suppose this is your ground state and this is the fast excited state 0 and 1. This is for your qubit 0, and this is for your second qubit ket 0 and ket 1. This is the ground state and fast excited state. And you are using this two particular qubit as a composite system. I'll introduce what composite system means and all, and how they are very different from the classical composite system, right? I'll come to that part. Now, in the physical hardware, how you are creating this part using a LC oscillator, for example, right? So choosing a particular L and C, and in a superconducting setting, how they act as an artificial atoms, and these are the energy level of that particular atom. And so using certain Josephson junctions diode and all. So so transistor, I can say. So basically, this is this A1, A2, A3, A4. They are not just some values that running on the air, right? They are the values which they have a physical. So information is physical, right? So this A0, A1, and A2, that the quantum state we have created, I can write it as a vector A0, A1, A2, and A3. So this is my quantum state ket psi, right? And this quantum state, this A0, A1, A2, A3, they are not running on the air. They are physical. The information is physical, right? So the hardware part, that is basically creating this A0, A1, and A2, they may have they may have certain noise, right? That may come from the thermal effect, because that is not an absolute zero temperature. There is some millikelvin temperature. One, there may be a different way how these basically amplitude A0, A1, A2, and A3 can vary slightly. That you cannot always produce the exact value every time, right? Because for the algorithmic reason, this will sustain for a certain time. That is the coherence time of the particular qubit, right? And they can vary. So hence, this state psi may not be perfect state. There may be some uncertainty in that particular state, and we'll be learning that uncertainty we can map as, say, psi1. First time I create psi1, second time I get psi2, and so on to psi n. These are the possible states, and every possible states may have a probabilities, associated probabilities p1, p2, and pn, right? So this is a description called the ensemble description of the system, and tomorrow we'll be learning a lot on this part, on this particular topic. And then you will see there is a different way of representing information called a density matrix row. Okay, so our input will be, instead of a vector, column vector, ket psi, we'll be writing as a matrix called a density matrix, and that density matrix can have a evolution, right? Now you can say, okay, if I don't have the uncertainty in psi, right? So this is a perfect psi. Somehow in future I can create a fault tolerant quantum computer that won't have any noise on a particular logical qubit. That's great. That time, by definition, it will be psi outer product psi, where psi is a perfect state. This is called a pure density, pure state, or the density matrix of the pure state. Okay. So these definitions and all, I'll come. but where I am staying. So my input is a state size, a row. I'm evolving over time, and I will have some state, say it is sigma, okay? And that sigma will be U row, U dagger. So this is the relationship we can create. So um so earlier I was having the state phi equals to U time the ket psi, and now my model becomes U row, U dagger. Okay. You can also prove it, right? How to prove it? Suppose your row is simply outer product of the state psi and psi, and this is your evolution matrix, okay, time evolution matrix, or the evolution matrix, and this pi is this one, right? Then what will be sigma? Sigma will be your outer product of phi and phi, right? So if outer product and phi, then you can always write it is as u psi right? Am I correct? So this part is direct, right? And this part is this one, right? So u this and this one, right? So this is u, and this is by definition, this is row, this is used, right? So this is how we model the same system in a different way. This is the noiseless. So now I just said, where is the noise coming, right? So I just told that noise can come here, right? But noise can also come here in the channel part, right? So till now, I haven't considered that the channel is noisy. Still, I'm considering the channel is noiseless, right? I'm only considering that the information I am encoding, there is a noise. And with only that particular part, my model becomes this one. So we'll formalize this part with something called Krauss operator phenomena. Okay, and there is something called the CPTP map. So that part also will be looking tomorrow. Okay, so now let's come back to our classical or quantum part in very easy way that we understand. So first of all, um, uh, some of you may face difficulty. For you, I'm just again coming closer to the basic part. So I can represent my quantum information ket psi for a 2-qubit system as alpha ket 0 plus beta ket 1, right? We have seen how to represent it and all huge details in the QT, probably 2 and 3 or 1 on linear algebra sessions that I have taken. So I'm not covering that part again. Suppose we are representing our quantum state with two basis systems 0 and 1, and alpha and beta are the amplitudes, where alpha and beta are complex numbers. What is happening? Are complex numbers, and alpha square plus beta square equals to 1, right? This is the y constant. And these are called individually, alpha and beta are called the probability amplitudes, and alpha square and beta square are called the probabilities. Probabilities of 0 and 1 respectively. Alpha square and beta square, okay? So for a system with more than two particular bases that we have seen, so that is, if I represent psi instead of alpha and beta, suppose this is a superposition of many bases, alpha I and I. This I can take any value, right, 1 to n. Then my probability amplitude will be alpha I square, right, for ith state, right? And this is by something called Born rule. So here, for example, for the 2-qubit system, we know that 0 is 1, 0. So why I'm covering this part, I'll come. This is important. In fact, why we particularly choose a particular basis. So these are just orthonormal basis vectors, because dot product of 0 and 1 will be 0, right? And the dot product with the same vector will be 1. So in Bloch sphere, this is 0 and this is 1. If you draw a Bloch sphere, so this is the plus basis, this is the minus basis, this is the 0, ket 0, and this is the ket 1, right? So opposite pole is 90 degree in the Bloch sphere, where in the Cartesian coordinate system, x and y coordinate system, this is the 90-degree angle. So now, uh, so this is the just simply a particular state, and then we know that if I represent a state psi, and my measurement is just projections in the basis 0 or 1. So if you project this state to 0, 0 basis, so 0 and 0 dot product is 1. So I'll be getting alpha as my output, because this is equals to, sorry. Right. So, um, so if this is my state, then I'll be getting alpha 0, 0 plus beta 0, 1. So this will be 0 and this will be 1. So it is alpha, right? So similarly, if I do my measurement, if I do measurement in the 1 basis, I'll be getting beta. And if I take square of that, I'll be getting the probability amplitude of that particular state, right? Now we'll be learning an important thing called the composite state. And this is very different from the classical state, right? Because classical state you already have seen in other lectures. So like I was drawing two atomic artificial the energy state of two artificial atoms. So if you have more than one like atomic system, we represent them with something called composite system. So multiple quantum systems can be viewed as viewed collectively as a single compound system. Okay. And this kind of compound system, or also known as a composite system, there are two types of such system. One is called the product state composite system. Product state composite system, and another one is called the entangled state composite system. So I'll come what they signify, what are the meanings of these two terms. Okay. So many of you have seen those who are working on the quantum simulation techniques for chemistry and physics problem. So suppose for you have an atomic configuration, say water molecule H2O, H2O. So I have drawn wrong. 2 hydrogen and 1 oxygen, right? Digital boards are time consuming often. So suppose you have 2 hydrogen and 1 oxygen case, right? So H2O. So by considering the orbital configurations of oxygen and hydrogen, suppose you come up with a Hamiltonian, right, that describe this composite system, Hamiltonian for these configurations as your H. Suppose this H is not the hydrogen molecule. This is the Hamiltonian H, right? So suppose let's write it as H1, for example. Okay, and you design a unitary matrix out of this by tautorization of certain techniques. This is your U. So this is H1 to e to the power IHT is the time evolution matrix, right? Now you will see that this is not a 2 cross 2 or 4 cross 4 matrix. This can be a big matrix, right? It can be n cross n matrix, and you may need more than 2 qubit, right? So especially if you work with Fe3s3 or this kind of thing or a bigger molecule. So this as the bigger molecule will be taking, so the dimensionality of this U will be bigger and bigger, right? And then can you decompose this matrix? Can you decompose this matrix into the smaller matrices? So you say SU2, right, as a product of SU2, like the Pauli matrices, for example, the sigma X product of this kind of matrices, 1, 0, sigma Y, 0 minus I, 0, or sigma Z, 1 minus 1, 0, 0, right? And in fact, the identity matrix itself, 1, 1, 0, 0, right? And some coefficient times this kind of matrices, or these are the 2 cross 2 unitary matrices of the Clifford set, and also known as the Clifford gates of 2 cross 2, right? Of dimension 2 cross 2. Or in fact, you can have certain 4 cross 4 gates like the CX or CZ, right? So for example, CX can be your 1 1, this 1 0 0 0 0 1 0 0 0 0 0 1 and 0 0 1 0. This is your CX gate, but this is the X part and this is the identity part I part, and this is the sigma X part. So that's why CX is written as your sometimes this is also defined as 0 0 outer product tensor product with I plus 1 1 outer product tensor product with sigma X. This is another definition of CX. Similarly, for CZ, this part will be sigma Z. Okay. So, and in fact, you can design any CU gate. CU gate also you can define as 0 0 tensor product with I plus 1 1, sorry, tensor product with U. Okay, so this way you can get a bigger, say n cross n matrix you can generate. But can you break this bigger U to smaller? All these are unitary matrix. In fact, a small unitary matrix, right? So these, if you can break this way, all these sets of the breaking thing is called the product state. And there are algorithms called the MPF, multi-product factorizations for this kind of algorithm, right? So multi-product factorizations kind of thing, right, for this kind of problem. So in general, we have two particular state. One is called the product state, and another particular state is called the entangled state. And let us deep dive with this. So first is the product state. Suppose phi is a quantum state. Suppose phi is a quantum state of a system X, and psi is another quantum state of a system Y, and their tensor product those who does not know about tensor product, this is just simply mathematical Kronecker product. Okay, So the tensor product that is phi tensor product with psi. This is also written as phi psi is a quantum state of the joint system x comma y. So if we have this kind of configuration, so now we have a joint configuration of atomic setup. It can be for photonic quantum system. If you have a photon, particular photon here, if you have another photon here, and this photon has certain polarizations like this, and this photon may have polarizations like this, and in general, this is the composite photon polarization state that you can define. And for superconducting, this is the state of the system. For spin system, similarly, you can think of. And then this is the joint state, right? That is the phi psi state. Phi psi state. Okay. And this is extremely important. And this particular state of this form, this kind of representation, we call the product state representation. This representation is called the product state representation. In fact, when we design algorithm, suppose you want to calculate um, the fidelity, right? What is the overlap between two quantum state, or what is the distance between two quantum state, right? So you have typical circuit like this. So you put a Hadamard gate here, and then you design a swap gate, control swap gate, and then you put another Hadamard, and then you do measurement, right? So this is the circuit to compute this phi and psi inner product. So this is called the swap test circuit. In Qiskit you can do it. But what I'm telling is that this particular part, when you just design this way, because you cannot directly get this psi and phi state, because they are created from some Ket0 state, right? You have some initialized qubit, say it is taking n1 number of qubit, it is taking n2 number of qubit, right? And then this particular part is called a composite quantum system or a product state. Composite product state. Product state. In fact, you can consider this together. And that's why the final state, we write it as 0 tensor product with psi, tensor product with phi, right? Also, it is written as 0 psi and phi. So this is the representation of a product state. Okay. And now, in general, if we have many such systems, right? So for example, we have a system like psi 0, psi 1 dot 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 psi n minus 1. If we have this many number of systems, right, then their composite system can be written as psi n minus 1 tensor product with psi n minus 2 dot 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 psi 2 psi 1 psi 0. So this is the product state of a composite system of in number of system, right? In number of system. So now, if this is the case, I'll give a break in 5 minutes. Okay, so just let's complete this part now. And then by definition, this particular state that is psi n minus 1, we can also remove these notations. We can directly write psi n minus 2, psi n minus 3, and so on up to psi 0. Right? This is a whole state, and the norm of this state will be equals to individual norm. So this is suppose 2 norm, right? Psi n minus 2, and so on up to psi 0. So that individual norm to validate a particular quantum state, then you have individual quantity will be equals to 1. So 1 to the power n number of systems, so 1, so it will be 1 by definition. Okay. Okay, I'm going a bit fast, so I'll be going slow from now. Um, Sorry. Let's go a bit slow. What is a composite quantum system? This is extremely important to understand because even before going to entangled state, I'm summarizing what is product state. So you have individual quantum system, right? Suppose you have a quantum system and that is represented by psi 1, for example, right? And you have another system, quantum system psi 2. So every individual quantum state that we prepare psi 1 and psi 2, because it can contain the information, say A and B, it can contains the information C and D, right? So if they are classical information, you can add them, you can multiply them, whatever you want, you can do them, right? In the classical setting. But in quantum setting, the so because classically you are just have certain voltage level or current level, right? That is creating A and B. Because this A and B, if they are classical, physically what you are doing, you are creating using certain not operations or certain operations, right? Like the CMOS based thing, right? So you have certain transistor here. So if it is a C naught configuration like this, so you have a PMOS, you have a NMOS, right? And here is VCC and here is ground, right? And if you give a high voltage here, you get a 0, equivalent 0. And if you give a low voltage here, you get a 1, right? That was our simple NOT gate using CMOS transistors, right? So then just you do another CMOS, you can add them, right? So suppose two informations you can create just by combining this kind of transistors, you can do whatever you want to do. That's on the classical part. But on the quantum part, you cannot simply do that. You created a quantum informations, right? And that is say using certain LC oscillator kind of thing, a superconducting transmode qubit, using this ground state and excited state. And suppose you created a state like this. Suppose this is your state, right? Which is a combination, superposition of this and this, right? I mean, this is just a, I'm representing this way. This is not the correct way because this is the vector way of note. I should do the notations, but in general, this is an independent quantum system, right? Similarly, you have another independent quantum system. Say this is psi 1 system. You have psi 2 system, but by definition, this psi 1 has to be has to follow all the quantum postulates, quantum formula, like their probability, sum of the probability equals to 1 and so on. Similarly on the psi 2, right? Now together we cannot simply add them together, they form something called a composite quantum system. Composite quantum system, right? And their joint representation is written mathematically as psi 1 tensor product with psi 2, this way. So this is the composite quantum system representation. So suppose what is a product state? Product state is something, suppose I called this state as a psi state, which is a product of psi 1, tensor product of psi 1 and psi 2. If I can write a composite state, right, as an individual product of tensor product of individual product of smaller quantum system, I call that particular system as a product state, right? But there is a special state, I'll just come back after this break, called the entangled state, which will violate this condition, right? But they are composite state, but they cannot be broken down to smaller pieces, right? Yes, this notation, this is called a Kate notation. There is a question. This is called a Kate notation. Say Kate Q or Kate psi, say Kate X. This is Kate notation. This is simply a column vector. Okay. Column vector. So in mathematics, you know row vector and column vector. So suppose you have a classical information, say 1 and 2, right? And you suppose created 1 by square root 2 and 2 by square root 2. This is your, suppose, normalized vector out of 1 and 2, right? And you encode it on the probability amplitude of the qubit. So you started the qubit as gate 0. Then somehow you have done something here, certain operations, then you created a state that is equivalent to that state, 1 by square root 2 and 2 by square root 2. And that is we are calling as QT-06. Okay. So with this very basics thing, I'm just giving a 5 minutes break. We'll come back and we'll study the entangled state in details. Okay. And slowly we'll see their implications. Okay. Uh, if you have any questions, please feel free to put in the chat box. Okay. So quantum information theory itself can take an entire semester, 40 hours, right? I'm covering it in 4 hours today and tomorrow, but I'm trying to cover the very basic concept because otherwise it will feel a bit difficult to understand the complicated concept, especially the quantum channel. And but don't worry, I'll be sharing you all the notes and all, so that may be helpful. There is a question. Explain the Hadamard gate representation of composite. Okay, I'll count to Bell state and I'll explain how it is happening. Okay, Hadamard gate is a single qubit gate. How can you represent as a composite system? This is not possible, right? A single qubit gate. But yeah, I mean that is used for creating the Bell state. I'll show. Okay, so this one, right? This Hadamard thing, right? You are asking how it is coming. Okay, I'll come this part. So I'll explain Bell state. At that time, I'll explain the role of Hadamard. Yeah, sure. I'll be sharing all the information. So we are just coming back in 5 minutes. Okay. Going for faster. So let's start maybe.
Yes, sir, we can start.
Yeah, thank you. So now let's start. I got one question on the Hadamard gate part. I'll come back and I'll explain. So now let's start the entangled state. Um, so not all quantum states of multiple systems or subsystems are product states. So we can have some states like this. For example, we can have a state, say E. I write it as get E, okay, as a state, like 1 by square root 2, 0, 0, plus 1 by square root 2, 1, 1. And this is not a product state, not a product state. Product state. You can ask me why it is not a product state. We'll give a proof. Okay, so you cannot decompose this particular state. Although this is a composite system, but you cannot break it to smaller subsystems. Okay, so let's what does it mean? First of all, what does it mean? So suppose this is equation number 1. Okay, this particular part. So if 1 were a product state, then there would exist, if it is a, if kit E is a product state, then there exist two particular states, say phi and psi, such that we could write this kit E as a outer product, as the outer product of phi tensor product with psi, which is 1 upon a square root 2, 0, 0, plus 1 upon a square root 2, 1, 1, right? Then then it would necessary case that if that is the case, then what is necessary? Necessary condition is 0 is if I take 0 phi outer product and sorry inner product and 1 psi inner product. Suppose this is the case, right? Which is a 0 1 state, because for two particular cube state like phi and psi, what are the possible states if they are individual quantum state? So they have the possibility 0 0 0 1 1 0 and 1 1. These are the four possible state, right? And one of the states is 0 1 state, right? So then I can write it as 0 times because the state phi I want to project in the basis 0 and the psi I want to project in the state 1, right? So then this is the inner product representation, right? I want to do the projection. So this is equivalent to, I can write it as 0 1 state, right? I am doing the projection of the composite systems phi tensor product psi. So I am projecting this composite system in this particular basis. I can represent them, and which is equals to 0 from the equation, because this particular equation does not in equation 1 there is no 0 1 state, right? So that means it has a probability of 0, right? And I can write it as this way, like 0 times phi and 1 times psi, which is 0 1. 0 1 is the basis state where I am projecting this particular phi tensor product with psi state, right? Which is equals to 0, right? And now it implies that immediately it implies that 0 either 0 times phi should be equals to 0, or 1 times psi will be equals to 0, or both. That is the condition if the product of two quantity equals to 0, individually they are 0 or both are 0, right? So this is the case. But if they are 0, then it contradicts that then if I do this 0 phi and 0 psi, right? This is the state I create, which is basically 0 0 state phi times psi. So that means if this is the case, then if I create this particular two quantity, which is basically projecting the composite system in this particular basis, if I project that particular thing on the 0 0 basis, and by this condition it is coming at 0, right? Because one of them 0 or both are 0, right? If that is the case, right? So then if it is equals to 0, but I have a particular probability, right? Probability of half, because the probability is the square of this square root 2, right? Probability of 0 0 state is half, but it is giving as 0. It contradicts, right? Contradicts the equation number 1, right? So hence we cannot do this, like otherwise either this is equals to 0, or I can write it as 1 this phi 1 psi, that is equals to 1 1 state if I do the projection of the composite system in the 1 1 basis, right? Phi tensor product with psi, which is uh, which can come as 0, but I have to get it as a half, or this is also equals to half, right? 1 by square root 2, 1 by square root 2. But if one of them is 0, then these particular two states are not coming, contradict with the fact. So this is the fact, right, from 1. So that's why basically I cannot decompose this kind of state into two individual state, right? So and that's why equation number 1 represents a strong correlation, between two system between two systems which you cannot divide them into individual states, right? That correlation is there, and specifically we call, or we say that the systems are entangled and they have a state entangled state KT, right? This is the case. You cannot individually break them, right? So let's do an alternate proof also. So this is a, if you feel this is a complicated proof, so let's do another proof, because so why I'm doing an alternate proof, because the quantity you are looking at 1 by square root 2 is not important here. Some of you may think, okay, if there is an entangled state, it will it has to be always 1 by square root 2 0 0 and 1 by square root 2 1 1. That is not the case. 1 by square root 2 is not important here. Okay, so 1 by square root 2 is not important. Not important to this argument. Um, and in fact, we have another example. For instance, suppose 3 by 5 ket 0 0 plus 4 by 5 ket 1 1, right? This is also another entangled state. Also an entangled state. Okay. So that's why let's do an alternate proof. Suppose I have a state phi as alpha ket 0 plus beta ket 1. And I have another state psi as gamma ket 0 plus delta ket 1, right? So the earlier proof was the reverse proof, and this is the forward proof. Okay. So then their paired state is phi psi. This is the composite state, right? And that will be your alpha. So just you need to do the tensor multiplication, and what will be getting? Alpha gamma 0 0 plus alpha delta, sorry, alpha delta. These pencils are always creating problem. Sorry for this. This will be gamma, okay? Alpha gamma 0 0. You are multiplying this with this. Then alpha delta 0 1 plus beta gamma 1 0 plus beta delta 1 1. Just multiplying these two vectors in the tensor multiplication form, right? So this is your composite system. But from 1, we have ket E equals to, the composite system is 1 by square root 2 0 0 plus 1 by square root 2 1 1, right? So that means it requires, so we have missing of this particular basis and this particular basis. That means alpha delta equals to 0 and beta gamma equals to 0. So product of two quantities 0, alpha delta. So individually either alpha equals to 0, delta non-zero, or both are 0. Similarly for beta and gamma, right? So either this 0 or delta equals to 0, or beta equals to 0, or this gamma equals to 0. If this is the condition, then from here, what we are getting, if we compare this particular two equations, if you look at this quantity and this quantity, they are non-zero. They are 1 by square root 2, 1 by square root 2, right? So alpha delta, alpha gamma not equals to 0, and beta gamma not equals to 0, right? Because they are 1 by square root 2. Hence, these two conditions contradicts each other, right? So we cannot, in general, this ket E cannot be broken as this 5 times psi. This is not possible, right? That's why this kind of states are called the entangled state. This is the entangled state, and these are strong correlation state. Strong correlation state. So this is extremely important, especially for those who will be working on quantum communications. Why we should create entangled pair between the transmitter and receiver. So tomorrow, if I get time, I'll cover something called the teleportation, and this kind of e-gate is called the one e-bit of information. This is called one e-bit of information, one entangled bit of information. Okay. So now we'll be studying certain entanglement, but I got one questions. So now you can ask me, okay, I cannot break this. Then how to create this state? How to create this e-gate? This is on a quantum computer. Okay, whether it is a photonic setup or it is a whatever setup it is, right? Okay, to answer that question. So let's take 2 qubit 0 and 0. So what is the state, composite state? What is their composite state? Their composite state is 0, 0 here. So this is your step, suppose step 0 here. Step 0, your state is 0, 0, right? Now I apply a Hadamard gate here. So what is the role of Hadamard? The role of Hadamard is if you apply a Hadamard in front of 0, it will create a superpositions and you will be getting the plus state, right? So plus state is basically 0 plus 1 by square root 2. So this is the purpose of Hadamard gate. Okay. If you apply Hadamard to 1, it will create minus state, which is 0 minus 1 by square root 2. In fact, you can do it by hand. For example, if you can't believe this, then a definition of H is 1, 1, 1 minus 1. This is a unitary matrix of this form, and 1 by square root 2 is the scaling factor for this, for the normalizations part. And yeah, I'm explaining the Bell state now only. Yeah. So then remove this 1 by square root 2 part. So H times get 0. So that means 1, 1, 1 minus 1 matrix time of vector 1, 0, right? And you'll be getting the state 1, 1, right? Which is actually get 0 plus get 1, right? So if you put the normalization factor 1 by square root 2, 1 by square root 2. So this is 1 by square root 2, and this is called the plus state. Right, just simply a matrix product, because 0 is basically 1, 0, and so 0 is your the state 1, 0, and 1 is the state 1, 0, 1, right? So if you plus, then you will be getting, so 1 and 1, so you'll be getting the 1, 1 state, which is the superposition state, right? So then if I have a, so what is my state here? So at step 1, what I'm getting in the circuit, so this is plus state, and this was already 0, right? So step 1 mathematically, zero plus 1 and tensor product with 0, right? So this is your step 1 equations, right? Now you create a special gate, you apply a special gate called a C0 gate. Right? C0 gate. So what will happen? This is at step 2, right? So in so if you break this state, what are the what is the vector representation of this? This is 1 0. This is your state just by breaking this equation tensor product form. So 0 0 and 1 0. This is your state. Step 2, you are applying C naught. So what it does is that the definition is 0 0 sorry, just a few minutes ago I gave the definitions of C naught, right? So it was outer product of 0 and 0 tensor product with identity plus outer product of 1 and 1. Pens, digital pens always create trouble. So I'm sorry for this bad handwriting. And this is the Pauli X gate, X or sigma X, whatever you write, right? So this is 0 0 state. Okay, so let me rewrite this again. Okay, so what is the purpose of this? If the first qubit is 0, it does nothing to the second qubit. So does nothing. If the first qubit is 1, then it flips the second qubits. Flips the second qubit. Means the information of the second qubit, right? So then this particular state will be, the first qubit is 0, so it will do nothing to the second qubit. It will be 0 and 0. But in this case, first qubit is 1, so it will flip the second qubit, which was earlier 0, now it will become 1. Right, so my state becomes 0 0 plus 1 1. So this becomes my state. But because of the normalizations, because I applied Hadamard, Hadamard has a normalization factor square root 2, right? And that square root 2 will come here. Yes, what is happening? And hence the step 2, the state will be 0 0 plus 1 1 by square root 2, right? And this configuration, Hadamard followed by a C naught, is called the Bell state circuit. Bell state circuit. Now at this particular point, this is the state E that we were talking. This E state, now you cannot break into individual state. This is the state you have created. And this particular state you cannot just break into two products. So that's why it is called a entangled state. Okay. In fact, there are 4 Bell states. There are 4 Bell states which are written as phi plus 1 by square root 2 0 0 plus 1 by square root 2 1 1 phi minus 1 by square root 2 0 0 minus 1 by square root 2 1 1. There is one question. C naught flips the second bit if control bit is 1. Yes, exactly. So that just you can do by math also. It will take consume some time. That's why I just skipped. I just applied the philosophy. Okay. So you can multiply this matrix with the vector. The vector is here, right? If you multiply these two things, you'll be easily getting this, right? Okay. And then there are two another Bell state, psi plus, which is 1 by square root 2 0 1 plus 1 by square root 2, 1, 0. And there is one more psi minus 1 by square root 2, 0, 1, minus 1 by square root 2, 1, 0. So how to create this state is a homework, okay? Using circuit. So I just have shown this step. Now you have to achieve this one, design the circuit. Now you don't have 0, 0 and 1, 1 state. You have 0, 1 and 1, 0 state, right? So where from shall you start? And such that your final entangled state is this one, right? Okay. This is also an entangled state. Now you can all see that the state that we have prepared, this phi plus, phi minus, psi plus and psi minus, all of them are using 2 qubits, right? So 2 qubits, of course, 2 qubits has how many states? Q0? I'm sorry, just the board is taking a lot of issues. iPad itself. Next, I have to. So a lot of latency is there. Okay. So 2 qubits, they can have state 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 state, and hence the qubit state will be 0, 0 kit, 0, 1 kit, 1, 0 kit, and 1, 1 kit. These are the 4 representation. And in fact, these are the orthonormal basis, right? Orthonormal basis vectors, and they are also computational basis. In fact, 0, 1 are called the computational basis, right? So that means if I have a coordinate system, Cartesian coordinate system I'm drawing, this is your the coordinate of this point is suppose 1, 0, right? And the coordinate of this point is say 0, 1, right? And you can write this vector as 1, 0 is your ket 0 and 0, 1 is your ket 1. Suppose in the Cartesian coordinate system, this is my ket 0 and this is my ket 1, and any quantum state, and I can represent in these two bases that this is equals to alpha amount of ket 0 plus beta amount of ket 1, right? This is the amount alpha and this is the amount beta, right? This is the way we represent information in vector form. So if I have a system, some 4-dimensional system, I cannot draw it in this board, but let me just for conceptual part. This is creating a lot of trouble. I'm trying to keep all the notes in one place. And suppose these are my 4 computational bases: 0, 0, 0, 1, 1, 0, and 1, 1. Right? 4 computational bases I have, and I can represent my information. Suppose my information is now it's not working. Let me take a new board maybe. suppose I have these four-dimensional places 0, 0, 0, 1 and 1, 0 and 1, 1. And suppose I represent my information as suppose this is my quantum state psi, which is alpha 0, 0, 0 plus alpha 1, 0, 1 plus alpha 2, 1, 0 plus alpha 3, 1, 1. So my information is stored in the probability amplitude alpha 0, alpha 1, alpha 2, and alpha 3 in this system. So this is one way of representing my informations, right? Now, now I created Bell state. In fact, I created a different representations where this was my original space, but now I have something else. What is that? I have created something using entanglement, and I have this kind, instead of that system, I have now this system where I have phi plus state, I have phi minus state, I have psi plus state, I have psi minus state. These are my computational, these are my orthonormal basis now, where individually they are entangled state, and I can create any state out of now I can represent my quantum information psi as some new way of writing beta 0 of phi plus beta 1 of phi minus plus beta 3 beta 2 of psi plus and beta 3 of psi minus this particular state, where now I stored my information in the entangled basis, right? So that's why this set of phi plus phi minus psi plus psi minus, this is known as Bell basis set, and this is extremely important. Those who will be in future, I guess, because there is no research paper as such in this domain, in this area, uh, those will be in future creating on quantum cryptography, right? Quantum encryption. And just I am giving a flavor that how it can be useful, because there is a person's Alice, say here, and there is a Bob here, and you have an entangled information scat E between Alice and Bob, right? Some entanglement pair is there, right? And in how many ways you can share the joint informations, because there is a single, suppose a photon is here to Alice and suppose a photon is here to Bob, right? And they have an entangled photon, for example, right? Now suppose Alice is, wish to share the information psi to Bob, right? In best possible way, because the information that will be traveled, it will be coming five because of the path, right? The fiber optics or whatever way it is coming, right? That is there, that the noise part that will be there, that is there. But however, how we can use this entangled pair E1, right, to securely transfer the information from place A to B, right? So this is some place of representing instead of the computational basis to the Bell basis, for example. Of course, in teleportation, this protocol is used. This is one of the very secured way of. There are protocols like BB84 and on. All protocols are there, right, for QKD specifically. So, but I mean, of course, when there will be quantum internet, specifically, you have multiple quantum processors connected each other. So, how you shared your information in the Bell basis set, right? Where you cannot individually measure them in the computational basis. That means outside this Alice and Bob, no one can measure the particular quantum informations, right? So um, in fact, why this is a valid basis set? Because any information, suppose 0, 0, some informations when you measure in the computational basis, you can also represent in the Bell basis way, phi plus and 1 by square root to phi minus, right? So because if you just see the definition of phi plus and phi minus, you can add this way and you will be getting the this particular state, and then you do the measurement, right? So then you will get the informations back in the computational basis. However, the way instead of this kind of addition, suppose you transfer the information in certain entangled pair way, how outside this Alice and Bob no one can interfere, right? This is one important research angle. So this is the 2-qubit entangled state, and let's see higher qubit entangled state, and one of them got the Nobel Prize in 2002, that is called the GHZ state. Okay. So this is named after three scientists. We all know their name. I'm just writing their surnames. Okay. So the Greenberger, Oni, and Zillinger. So GZ is named after these three scientists who got Nobel Prize in 2002 to to work, study, and so demonstrating this on the laboratory, right? So this is an entangled state that involves at least three subsystem. Entangled state of at least three subsystems, or qubit, you can say. In our language, qubits. Okay, three or more qubits if you can create the entanglement pair, right? Um, so so there was a study. Actual study was 1889. Okay, and it would. So there is a exact sentence I'm copying from the research paper. So that the author wrote, it would lead to striking from their experimental result. They commented, because the experimental part mostly was done by Jellinger, and the initial theory was devised by the Greenberger and Horney, and they come to the conclusion that it would lead to striking non-classical correlations. So this is a non-classical correlations, okay, inconsistent with. So physicists a priori they have a theory, and that is called local hidden variable theory. In fact, this study was extended by two scientists. So one is known uh, Simoni, most likely. Please check the spelling. And another one is David Marmin. Okay. So this is David Marmin is also popular. You can find his textbook also. You can read his textbook. So great author also. You can read his books on quantum information theory by David Marmin. So they also studied extraordinarily on these multi-qubit entanglement, and this entire study was like celebrated with Nobel Prize in 2002. Okay, so sorry, 2022. Okay, 2022. And this state, GHS state, is written as for 3 qubit as 1 by square root 2, 0, 0, 0 plus 1 by square root 2, 1, 1, 1. So I'm not giving example, just in Google type Qiskit, okay? Qiskit plus GHZ state preparation. So all the entire circuit is there. Like the Bell state circuit I demonstrated, similarly, you can create this GHZ state in our IBM simulator or IBM quantum hardware. Okay, this is also possible. Okay, now for M-partite system, you can create a GHZ state as, so how many qubits are here? 3 qubits, right? So if you have m number of qubits, M-partite system, so you can write it as 0 tensor product M plus 1 tensor product M, right, divided by square root 2. Okay, this is a GHZ state of M-partite system. Okay, so this is also higher qubit entanglement, right? And there is something called a W state. This is another multi-qubit entanglement. and any state W multi-qubit is represented as 1 by square root 3 0 0 1 plus 1 by square root 3 0 1 0 plus 1 by square root 3 1 0 0. Okay, so this is another 3-qubit entanglement pair that we can create. So there is one question or request, sir, kindly deal teleportation and QKD at a. Okay, so teleportation I'll try to cover tomorrow if time permits, besides the no cloning theorem and all. QKD, I'm very sorry, I'm not a person in QKD, although I know the basics and all, but I don't feel myself as a persons to deliver QKD, because I think there are better persons to deal on QKD and they'll be teaching, and I'll highly appreciate their lectures. Okay. Can you simulate n-qubit entangled state? What is what is the highest value of n on our current 3-qubit you can create, okay, on current hardware devices. Multi-qubit people are doing research. I am not very sure, but of course theoretically possible, but practically how hard is that? Those who works on this topic, they can comment, because I do not deal directly with this area. Now we have another 10 minutes. So please put all your questions in the chat box. I'll answer questions, as well as I'll be covering another certain very basics, but very, very interesting thing regarding measurement specifically. We'll be coming to the measurement part. That is very, very important topic for us. So I what I introduced, just those things are will be required here. So the purpose of X gate, the poly X gate, is to convert the 0 qubit to 1 qubit, like the qubit gate 1, right? With the information gate 1. Similarly, if you apply poly X gate or sigma X, you can write this way also. They are same thing. X and sigma X are the same things. The matrix 0 1 1 0, right? Earlier I just wrote. So this will again make it to get 0 state, right? And all the operations that you do, whether it's Pauli X, Pauli Z, whatever it is, they are unitary matrix typically. And by definition, U dagger equals to U dagger U equals to identity. That means the definition is U star equals to U inverse. Dagger and inverse, just plus or inverse, the asterisks, these are the same notations, okay? Just using this way. Now, the purpose of Hadamard gate, so if I have 0, I apply the Hadamard, I am getting the state plus. If I have state 1, I apply the Hadamard, I get minus state, right? And now these are the states. Now they are important. Why? So whenever I am multiplying, whenever I am applying the, suppose I start with the X and then apply a X gate in the quantum circuit and I'm getting gate 1, right? Similarly, I am applying 1 on X gate on 1 and I'm getting gate 0, right? So, and then if you apply the X gate on the plus basis, you'll be getting the plus basis. And if you apply the X on minus basis, you'll be getting minus of minus basis, right? This is, you can verify. So because plus basis is basically your 0 plus 1 by square root 2, right? So if you apply the we are fascinated by Brian Greene teleportation document, is it? Yeah, that is a very nice one. I haven't seen in detail. I'll check it. Yeah. Sir, in classical, there is a proof of for and or X or etc. Like that, there is any proof for Pauli X, Y, G, C naught gates? What proof you are asking? Yeah, exactly. These are the gates here we are using, like the Pauli X, Y, Z, C naught. These are the quantum logic gates. And these are universal quantum logic. Sorry, these are reversible quantum logic gate, means unitary, used U star equals to U inverse. But the classical gates may be reversible, may not be reversible. That is the case. Okay. You can prove that way also. Okay. Now, if you apply the, suppose on the plus state, if you apply the X gate, then this 0 will become 1 and this 1 will become 0. That means the state will be plus, there will be no change. But if you apply X on minus, so then what will happen? So 0 will become 1 and 1 will become 1 will become 0. But the sign you have to take outside, that means this one. So this equation is following X equals to lambda X equations, eigenvalue equations, right? And lambda, here it is lambda equals to plus 1, lambda equals to plus 1 eigenvalue, and here lambda equals to minus 1 eigenvalue, right? That's why the plus and minus, this particular basis are called the eigenstates, are eigenstates of the operator X, right? And why I am, okay, so I mean, all you have simple property. This is all the quantum logics that I am covering. They follow simple Clifford and non-Clifford algebra principles. That means simply they obey all the properties of unitary matrices. The way you can do that means if you have two unitary matrix, product of two unitary matrix is another unitary matrix, but addition of two unitary matrix may not be another unitary matrix. You can check it. Okay, that means the addition operations you cannot do, right? You cannot simply add two gates like this X plus X, this way you cannot do, right? So that will violate the quantum operations, because the probability amplitude may not be sum equals to 1. Suppose the probability of one state is 0.7, another is 0.6. If you simply add these two quantum state, 1.3 is the probability. That is not a valid probability. So that's why you cannot do that way, right? So you cannot simply represent the quantum operations in the classical way. Okay. Now, plus and minus are the eigenstate of the operator X. Now, why this is important? Because suppose in the transmitter side, I transmit the data 101 and I receive the data, say my basis, I got the information 011. So there is a bit flip, right? So this last bit 0 flipped as 1, right? There is a bit flip error, right? And if there is a bit flip error, how to detect that there is an error in the informations, right? So how to first identify that error, because all the measurement that we see in quantum mechanics or quantum computing, they are the eigenvalues of the observable, right? So if I, in fact, the measurement operator that by which we see the particular quantity, right? The eigenvalue of that. So eigenvalue, if I want to see the eigenvalue plus 1 or minus 1, and if I can detect, okay, there is a minus 1, that means there is a bit flip. That means there is an error happened, because what A has transmitted, B may not know, right? We will only have this information, and if you operate some set of Pauli string on it, right, and you see, okay, there is a basically sign change, right, then you can detect, okay, there is a bit flip, right, by using the expansion of the informations in the eigenstate of Pauli operator, right. So this is a great way of understanding the bit error of the transmitted signal or the transmitted informations, right, using the Pauli bit string or the Pauli string. Okay, so there are two kinds of error in classical communication. Classical communication, there is only one error, that is you have, suppose the classical information that we have, we can transfer, say 1110, this is the classical information, and you can have 1101, suppose this is the thing. So that means there is one error, there is one error. This is the only source of error in the classical informations if you represent in the bit string form, right, in the binary bit string form. But quantum informations can have, suppose you are writing 1 and 0, right? You can have two types of error. One is the thing that is 1 and 0 and 1. Of course, these two bits are flipped, that is called the bit flip error. But there is a phase also. First qubit may occur a different phase, may incur a different phase, right? So there is another additional error may come in the quantum quantum information that we transfer, or the quantum communications, right? And that particular error is called the phase error, right? To model the phase error, we need to also deal with something on the Z basis thing, right? Z basis representation, or the Z operator form. So I'll just take the Z operation thing, and then I'll conclude the session. Okay, there is one question. Quantum systems operates in Hilbert space and classical system in ordinary Euclid. That is a phenomenal difference in physics. Maybe I mean, that's how you can represent, but in general you can also represent classical informations in on Hilbert space. That's a, I mean, uh, okay. So how you operate in simply is that the quantum informations should follow all the quantum postulates in just one sentence answer, because those postulates are required to validate the system design part in quantum communication. So now the Z basis part is that we have the Pauli operator Z, and the Pauli operator Z is defined as 1, 0 and 0 minus 1 this way. And now what is happening? And the plus state, is basically 0 plus 1 by square root 2. So now if we apply the G the G operator, the Pauli sigma G operator, also you can write this way. This is a G, same thing. On the plus state, you will see this will become minus. Okay, just simply you multiply this matrix with this vector, you will be getting minus, and if you apply on minus, you will be getting plus. So for the so this plus and minus are called the superposition basis. Superposition basis, or in fact for 2 qubit system, sorry, for 1 qubit system, these are in fact the Fourier basis, because the Hadamard gate itself act as a Fourier transform for 1 qubit that we have seen in QT-05, right? So so if you apply the G operator on plus, you are getting minus, and if you apply G operator minus, so it is giving plus. So it means if you represent your information, so in plus and minus basis, superposition basis, what I'm telling you is that if your information, so this is the Bloch sphere, right? This is the plus basis, this is the minus basis, this is the Ket 0, and this is the Ket 1. Where you are representing your information here, if this is your quantum state, you are representing with the Ket 0 and Ket 1. Suppose this is your alpha Ket 0 plus beta Ket 1. Then the bit flip you are measuring with the X basis thing, right? This is the bit flip error. But suppose you are representing your information here. Suppose this is your state phi, where phi is your gamma plus state plus delta minus state, right? So now you are only here in this plane, right? So if you are here, then G operator itself is doing the bit flip operations for the plus minus basis set. This coordinates this basically reference system. But for the computational system, because in general we do not represent the information directly on the eigenbasis, I mean the Fourier basis or the superposition basis, but we typically represent our any information in the computational basis. That means 0, 1, this kind of system, right? In this way, this is the way normally we represent our informations. So what is the implications of that? So if you apply G operator on 0, you'll be getting 0, and if you apply G operator on 1, you'll be getting minus of 1, right? So this is like the eigenvalue, this is the eigenvalue equation. So this is like Ax equals to lambda x equations, and lambda equals to plus 1 here, and lambda equals to minus 1 here, right? So that means if there is a phase change in the information, there is a phase error in the informations, right? So you can directly use your computational basis as a reference system, and you can identify, okay, there is a phase error in the quantum informations, and you can model it using the G operator, right? So that's why G operator is known as a phase flip operator. Phase flip operator and X operator is known as the bit flip operator. Bit flip operator. Now, if I ask in the question or somebody asks in the question that G operator, when the G operator will act as a bit flip operator in terms of the, if I represent the information in the plus minus basis, right? That means in the superposition spaces, then G operator can itself act as a bit flip operator and X operator will act as a phase flip operator. So the definition of phase flip operator highly depend how you represent your informations, either in the 0-1 basis or the plus minus basis, right? That is extremely important. Whether you are representing in 0 and 1 way, like this is your orthonormal basis set, or you are representing your information in the plus minus basis system, right? This way. So largely depend. If you are representing here, then G operator is your bit flip operator, X operator is your phase flip operator. You are representing your information in the computational basis system. This is the general way we represent in general. Then our normal definition is G is the phase flip operator and X is the bit flip operator, right? So with this, I conclude the sessions here today, and we'll come back tomorrow and we will start directly from the density matrix approach. Density matrix and channel.
Thank you very much, sir, for the interactive session. I think the all participants are here be listening you. So we will meet tomorrow at 3 p.m.
Yes, sir.
So thank you all the participants. Thank you, speaker. Okay. Bye.
Bye. Bye, everyone. Thank you for your presence.